in this video, we're going to look at the fundamental theorem of calculus part 2. Right? So here, this portion is going to talk about what is the derivative of an integral, right? Which seems a little bit strange. But if f is continuous on an open interval I containing a, then for every value of x in that interval, the derivative with respect to x from a to x of f of t dt is f of x. So let me see if I can give you a little bit of intuition. So here, that integral, if we were to think about just applying the fundamental theorem of calculus, you would find an antiderivative. You'd plug in the upper limit, subtract what you get when you plug in the lower limit. Right? And then what are you going to do with that? Well, we're taking the derivative of that. And so the derivative of that, f of x, the derivative of capital F of x is little f of x. And f of a, that's just a constant, and so that's going to go away when we take the derivative. So we just get f of x itself. Now, what happened here, or what this looks like happened, is that value of x, we just replaced the t with x. Oh, that's kind of fancy. All right, so let's look at some examples. And so here, we want to find the derivative of this thing. All right, so we want to know what is f prime of that thing. What is the derivative of the integral from 2 to x, t to the 5th, sine t dt. And that seems pretty difficult, right? Because we would say, what is an antiderivative of this? And we don't have the tools to find an antiderivative to this thing yet. But it turns out, since we're going to undo taking that antiderivative, it doesn't actually matter. We're going to end up with x to the 5th sine x. That's going to be our answer. Right? This x is going in place of that value of t. That bottom limit was just constant, so we would take the antiderivative, we'd get a constant, but then when we take the derivative of that constant, we would get 0. So this is what we have for the derivative of this thing. Right? That's applying the fundamental theorem of calculus, part 2. Now, we can generalize this a little bit more, right? So by the chain rule, if we are integrating from a to h of x, this derivative from a to h of x of f of t dt is going to be f of h of x. But then the chain rule tells us we also need to pick up an h prime of x. So this is the derivative of the outside. And this is the derivative of the inside. So let's see that in action. Let's see that in an example. So here we want to find the derivative if f is defined as this integral. So we're taking the derivative of the integral from 0 to sine x of t plus 2 dt. So we can replace the t with that function, sine x. So we have sine x plus 2. But we're not done yet, because now we need to multiply that by the derivative of that function sine. Derivative of sine is cosine. That is our derivative. Excellent. So let's look at one more example. And here we want to find the derivative of g of x, where we have the integral from x to 3 minus x of t squared plus 4 dt. Now this is a little bit different because that lower limit of integration, it is variable, right? That's not going to give us a constant. So how do we deal with that? Well, the way that we're going to deal with that is we're going to split this up. let's split this up at 0. So we have the integral from x to 0 of t squared plus 4 dt plus the integral from 0 to 3 minus x, t squared plus 4 dt. And then we will flip the limits of integration on this first one. When we flip them, we negate that integral. And now we can apply our fundamental theorem of calculus, part 2. So if we take the derivative of this piece, it is going to be the negative of x squared plus 4. And if we take the derivative of our second piece, this piece, it's going to be 3 minus x squared plus 4 times the derivative of that power. The derivative of 3 minus x is negative 1. And that is our derivative using the fundamental theorem of calculus, part 2. All right, come back for our next video. We will look at even more examples where we are going to apply the fundamental theorem of calculus, part 2. We will see you there.